So this is Margaret Hamilton. Now, if anybody doesn't know who Margaret is, you probably should. We don't get to be doing what we do in like talking about this kind of stuff, doing this kind of work, having an event like this, if Margaret doesn't exist. Before her, software engineering wasn't really considered an important discipline. It was certainly considered to be less than anything that's hardware related, certainly less complex and less significant. It was, you know, the work that you gave to the lesser folks. And she really fought against that. She was the first person to use software engineering as a term. She really advocated for like, hey, this is actually an important thing that we need to focus on and pay attention to. And her work was influential in really sort of kickstarting that. So anything that software engineering or a derivative of like that, like the web development, front-end engineering, all of that kind of stems back from her. She also had one heck of a resume. In the late 1950s, her husband enrolled at Harvard Law, so she took a job to support the family at MIT. Not a bad place to, I guess, if you're just looking for a job to support things. Her first job there, her introduction to computers and to programming was to develop and program a system that did weather analysis and prediction. Just to sort of compare and contrast a little bit, because I always think that's kind of interesting. My introduction to computers and programming was to build a web page that had bouncing basketballs in a spinning email GIF. Yeah, so pretty much the same thing. I would like to point out that I have, if you notice in the bottom right corner, there is a Lightspan StudyWed Academic Excellence Award. I remember getting that over email and I was very excited. I don't think Margaret got one of those. But no, so this was her start, was predicting weather. And then 2 years later, she was writing software to detect enemy aircraft. So I suppose if your introduction to programming is building a complex weather analysis system and detecting enemy aircraft, you probably get a little bored. You're looking for something a little bit more challenging and complex. So when a job opened up for her to start developing software to send people to the moon, she jumped at the chance and took it. She started writing software for, at first, unmanned Apollo missions. But what she's probably best known for is leading the team of engineers that built the software that powered the Apollo 11 mission that got Neil and Buzz to land on the moon. The Apollo 11 spacecraft was comprised of 3 modules. There's the command module, the service module, and the lunar module. The command module, that's where the crew sits during the mission. It's what they fly up to, and it's also what they return back to the Earth in. The service module is kind of the dumb box out of the 3, but also very critical. It housed the engine, the fuel, the oxygen, the electricity, the water, you know, the things that kept everybody alive. Together, they were the CSM, the Command Service Module, a very creative little acronym. And then there was the lunar module. And this is what actually makes the final trip to the moon. And then when the team is done on the moon's surface, this is what returns back to the command module, which again, they use to return back to Earth. Now, as you can imagine, sending people off to the moon for the first time is probably a little bit nerve-wracking. There's a lot of variables, a lot of risk. They wanted to make sure that navigation was precise. There was no room for error here. So both the lunar and command modules were guided by an Apollo guidance computer, an AGC, to help navigate to the moon and back. This little computer was, by any possible measure, far from potent by today's standards. It had 4 kilobytes of RAM and 74 kilobytes of ROM. So just to put that in perspective, this little computer that guided everybody to the moon and back had 0.1% roughly of the RAM in the iPhone 11. With constraints like that, you don't have a lot of wiggle room. Every single byte matters. And so Margaret and her team had to be extremely efficient with their code. You can find the source code actually on GitHub. So if that's your cup of tea, it's kind of fun to look through. The code for each of the AGCs in the repository is about 1.7 megabytes, but that number is inflated because if you look at the actual code, you'll see all these comments included. These comments were obviously not included in the original code. They were actually written on the hard copy of these modules for documentation purposes. They've just been added to the GitHub repo so that we can benefit from sort of, you know, learning a little bit about, you know, their process and what they were going through. So the reality is that the code base is actually much, much smaller than this 1.7 megabytes. So to me, this is a really remarkable bit of engineering. less than 1.7 megabytes of uncompressed code to program software capable of landing us on the moon. It's fantastic work. It is impressive. The median mobile site ships 2 megabytes of uncompressed JavaScript. Now, I know it's a little bit different. You have different languages, more verbose syntax, all that jazz, different stuff going on. I get that. But I still find it extremely humbling. 1.7 megabytes of code to send people to the moon. Meanwhile, 4.2 megabytes of code so that people can read very questionable dog facts. Harry Roberts posted an image on Twitter of an Imager waterfall from their mobile site. And it's a lot. There's a lot going on these little pages to display these images. We ship an incredible amount of JavaScript, and JavaScript is byte for byte the most expensive resource we have, because the wonderful thing about JavaScript is that you pay a performance tax 3 times, probably 4. I suspect memory is an issue that is running rampant on the web, particularly on anything that's, a single page architecture powered in Vue or React or anything with a lot of JavaScript running. I pretty much guarantee we've got memory issues lurking about, but the tooling's not quite caught up to where the tooling is on processing and things like that. So I suspect there's an awareness issue there. But we'll kind of leave that out for today. So let's just say that there's 3 times that we pay the performance penalty. The first is the network cost, right? We have to pay a cost for actually sending down that JavaScript over the network to the device. Then we pay the cost on the device when that code gets parsed and compiled and turned into something the browser can run. And then finally, we pay a cost when that JavaScript gets executed. So there's a 3-time payment. So I want to start with the network side of things. If you look at the data from HTTP Archive, which was referenced, I know Sia mentioned that from the images perspective earlier, it's a fantastic resource, tracks millions of pages and gives us all sorts of great information about those performance and otherwise. But if you look at that data and break it down into percentiles, we are currently sending 413 kilobytes of compressed code over the network to a mobile device at the median. At the 90th percentile, it's over a megabyte. Desktop and mobile for compressed code seems to be about the same. We were shipping pretty similar amounts, a little bit more on desktop, not a big reduction though for mobile here. So again, this is compressed, which means that we have gzip or Brotli or something like that applied, because when we pass JavaScript over the network, we can compress that text to save a few bytes. But there's a cost associated with this in terms of time, like transfer time that comes with this size. But what's more interesting to me is the data impact, something that was kind of brought up today a few times earlier by Aaron and Taylor. There was a great talk last year. Kenji from Google showed some Chrome metrics that they had. And they had this really weird pattern of behavior that they're seeing in Japan. So what you're looking at here is a chart that shows January through October, and it's tracking page load time across all of these Chrome sessions. And what you can see is each month, at the start of the month, the page load time is small. And as the month goes on, that page load time steadily increases until it peaks right at the end of the month and then drops back down at the start of the next month. So we see page load time dramatically increasing as the month goes on. The same Chrome data also tracked engagement. So, how many pages are people looking at? And if you look at the number of pages per users on these devices, you see the inverse happening. So at the start of the month, they're looking at quite a few pages. And as the month progresses, they're looking at less and less until it bottoms out towards the end of the month. There's only one month here that doesn't follow that pattern. So what's happening here? We have page load times increasing. We have engagement dropping, both of them doing it dramatically. So it turns out it's data caps. Data caps are something many of us are dealing with, but it seems like apparently in Japan, contracts line up a little bit more typically at the start of the month and end of the month. They're a little bit more predictable, whereas we might have contracts kind of, my contract might expire next week and yours a week later or something like that. So what's happening in Japan is towards the end of the month, as these data caps get hit, connections get throttled. And the load times start to go up dramatically and people use the web less. It's been brought up a couple times again today. I know Phil mentioned it a little bit too, in terms of like the impact of like right now with everything going on and the increased web use. I think this is a really important reminder that data still matters significantly. which I think is very important because as Ire mentioned this morning, like we've moved to these, we've got these great metrics. We've had this fantastic shift in the community where we've gotten a lot more sophisticated about how we measure performance. We don't pay as much attention to things like load time and stuff like that. We focus more on things that are about how does the user perceive the page? How do they perceive how your site or application is performing? But a side effect of that, unfortunately, is that we kind of lost focus on data a little bit. We don't bring that up quite as much. In fact, I remember distinctly several presentations that were early on in this sort of stage of like, hey, we're just now starting to, let's focus on how things feel, would point out examples of sites that would load megabytes of data, not JavaScript, just data in general. And their load time would be slow, but the perceived metrics looked really, really good. And this was like a model of like, oh, hey, see, it doesn't really matter. You know, what matters is how it's perceived. But this is a concrete example of, and honestly, everyday web use today is a concrete example of how data has a cost and data does have a consequence. So that network stuff isn't free. That being said, I want to focus a little bit more on the device. The network data is interesting and it's important, but it's also a little bit misleading. It's not quite a vanity metric to say, oh, we're shipping 200 kilobytes of compressed JavaScript, but it's close-ish. It doesn't sound awful, right? Like maybe you saw that 415 kilobytes at the median for mobile and you're like, that doesn't sound that bad. That seems reasonable. But most of the cost of JavaScript is incurred on the device, not the network. Increasingly, the sites that we build today aren't bound by the network. It used to be that was the limiting factor in performance. Not even that long ago, 5-6 years ago, it felt like. Nowadays, though, for most sites, the limiting factor for performance is the device itself. We're CPU bound because we're throwing high resolution images and lots of scripts and things like that at the device. And so when we look at the on-device cost of this script, it's much more problematic. So again, going back to the network cost, we had that 415 kilobytes or so at the median for mobile, that, you know, a little over a megabyte at the 90th percentile. But we want to see what this actually means for the device itself. So on the network, we get the benefit of compression. On the device has to deal with the raw code. It has to deal with all of that stuff. So the compression doesn't save us anything there. Studies around gzip effectiveness show that for JavaScript, you're typically getting a 5 to 7 time compression factor. So let's say conservatively that our uncompressed is only about 5 times larger. That means that the uncompressed script size that we're shipping down looks something like this. At the median, we're shipping 2 megabytes of code, as we mentioned earlier. At the 90th percentile, we're shipping 6 megabytes of code down to a mobile device. These numbers start to be a little bit more scary. They start to be a little bit more eye-opening, and I think a little bit more realistic assessment of the situation. But even more startling is what this means in terms of processing time. Because again, the device has to parse and compile and execute this. So HTTP Archive does collect this data for both desktop and again, mobile using these emulated Android devices. So we can look at how much time does Chrome in this case spend dealing with JavaScript on the main thread of the browser during the initial page load. The key point here is it's not after page load. It's not as people are interacting with the page. It's just from the time that you make that initial request to when the page is finished loading, how much time did the browser have to spend dealing with JavaScript? And those are where the numbers start to get a little unsettling, in my opinion. Again, at the median here, now we see a big difference between desktop and mobile, by the way. And at the median, we're seeing 830 milliseconds of JavaScript time from the desktop, which may or may not scare you depending on how hardcore you are into performance. At mobile, you're seeing 2.3 seconds. And at the 90th percentile, that is a whopping 10.5 seconds of JavaScript work being done by the browser. Just JavaScript, nothing to do with parsing the HTML, nothing to do with anything related to CSS or anything like that, purely dealing with the scripts. Those are really, really big numbers. Getting back to both Aaron and Taylor, I thought did a really good job this morning. I love their presentations, highlighting the various constraints and really hitting hard like how the device type and all these other characteristics really impact data and impact performance and how it can be very different from one situation to the next. And this data supports that. If we look at that 90th percentile, The mobile experience is 3 times slower. We're spending about 3 times more time dealing with JavaScript on these devices than desktop. And again, based on the emulation they're using, they're probably not even reaching those $100 devices or $200 devices that we talked about. So there's a big discrepancy here between desktop and mobile. So if we're building on our laptop devices, we're building on our MacBook Pros or whatever it happens to be, we're going to miss all of this. Things are going to look okay. They're going to look rosy. And really what we're shipping out is unusable to a large percentage of people. The device plays a massive role. And so does the technology. I thought one of the other things HTTP Archive does is it lets you detect libraries. So it'll report like, hey, we detected React on these sites. We detected jQuery on these sites. So I thought it would be interesting to take the mobile numbers here and use that as a baseline and compare that to some popular frameworks just to see, what are the characteristics? If a site's using jQuery, how much different is that from a site that, the baseline or a site that uses React? This is the data for that. This is what happens to main thread processing time as you use different frameworks. Now, the first thing that's probably going to jump out at you because they're scary big numbers is that 90th percentile. So our baseline was 10.5 seconds, which by itself didn't sound great. Impressively, jQuery sites seem to be a little bit faster at the 90th percentile. Keep in mind with all of this stuff, by the way, this is not necessarily saying it's React or jQuery or Vue that's doing all of this work, just that sites that have these libraries tend to correlate to a little more or a little less JavaScript processing. So jQuery sites seem to correlate to a little bit better in performance at the 90th percentile. Vue a little bit slower, about 2.5 seconds slower, which I guess compared to 10.5 doesn't sound that terrible. React is the one that really scares me. That's 20.8 seconds at the 90th percentile dealing with JavaScript, which is a massive number. Nobody's going to sit through that. But the 90th percentile is those scary big numbers. But the thing that really bothers me about these numbers is the 10th percentile. I chose a 10th percentile here because I wanted to see if 90th percentile starts to represent how bad can things get, the 10th percentile should give us an indication of how good can things be. We could have gone with a smaller percentile, maybe the 5th or 1st, but I figured you'd probably get some weird anomalies in there. So, I thought 10% is reasonable. If you're in the top 10%, you're doing pretty good. But at the 10%, we're spending 2.7 seconds dealing with JavaScript on React-driven sites. We're spending, 7 times more time dealing with JavaScript when we're using something like React than we are as our baseline. Everybody's a little bit slower. Vue's, 3 times as slow as the baseline. jQuery is a little bit slow. If this reflects as good as it can get, I think we have some problems. I feel like it's fair for us to expect more of our tools. I feel like it's fair to expect that a good framework isn't just going to give us the developer convenience. A good framework is going to help us to improve performance or accessibility or security, those foundational fundamental things, by either doing something to help limit how bad things can get or providing some reasonable defaults that make it pretty easy for us or give us a really nice starting point. And unfortunately, the data right now doesn't seem to support that either of those things are happening. Point blank, right now, if you're using a client-side framework to power your site, you're starting out behind. Now, you may decide that trade-off is worth it. And it totally could be. There's perfectly valid reasons why these architectures make a lot of sense. And there's perfectly valid reasons why you may say that, yes, I'm willing to make a little bit of a trade-off here by using one of these things. But I think it's important for that to be a conscious trade-off. I think sometimes we reach for a tool, reach for a new hammer, as Phil mentioned it, without sort of realizing what we're trading off in the process. And I think that it's important that we make sure that we're aware of that trade-off and aware of what we're giving up when we're deciding to use one tech stack versus another. And again, not to say that you can't make these tech stacks performant. In fact, we're about to talk about ways that you could potentially do that. But if you're going to choose one of these architectures, know that you're going to have to invest some serious time and energy into making sure that the performance is at a high level. So all of this processing time manifests itself in these long-running tasks. Long-running tasks being anything 50 milliseconds or more. This is a profile on my MacBook Pro with a 4-time CPU throttle. When you're running any profiles on Chrome DevTools, I highly recommend throttling the CPU every time. Again, we're on pretty powerful machines usually, so we're going to miss a lot of performance issues. At least a 4 times throttle to sort of surface some of those things that might be kind of lurking underneath. Small caveat right now, when I run CPU throttling and Chrome DevTools, it keeps crashing my browser. Hopefully that gets fixed soon. But this is a profile of a React site in this case. And there's a bunch of long tasks, all the red marks that you see across the top, as well as the little triangles in the corner of the flame graphs here. That's Chrome telling us, hey, these are some long running tasks that are over 50 milliseconds. You should look at them. This pattern is pretty typical, where I see a really large task up front to execute and evaluate one of the initial bundles being delivered. It's a really common pattern for any single page architecture. In this case, what we're looking at is 2.5 seconds of work. And if you look through the flame chart a little bit, what you find is that it's React work. It's React getting things set up, you know, hydrating the DOM with its synthetic event listeners and getting everything kind of connected and stuff like that. That's a huge chunk of time, 2.5 seconds, where the browser can't respond to anything else. Now, there is work being done around progressive hydration inside of React that would let us choose to hydrate certain parts of the DOM right away and then hydrate other parts later and sort of break this up a little bit. And I'm really excited to see that become more robust and get rolled out. I sometimes wonder, you know, how many of these problems we're inventing only to have to then invent the solutions to them. But that's probably a discussion we should be having after all of this goes away and we can meet and have beer again. So yeah, the long tasks, a pretty common symptom of anything with a lot of JavaScript, and it's one of the first things I recommend tracking on any site, really, but any site, especially things that have a lot of third-party content or a lot of JavaScript being run through a single-page architecture or something like that. Observing them yourself is not terribly difficult. You can set up a performance observer. In this case, what we have is we're checking for any performance events being triggered that are long task types. And anytime those come in, we're going to queue them up and we can send them back to tracking somewhere. If you're using any sort of real user monitoring solution for performance, anything like speed curve or impulse or you know, perfume or stuff, those sorts of things should be handling long tasks for you. I think it's interesting because we haven't quite figured out the best way to keep tabs on long tasks. There's a bunch of different approaches out there. So this is a totally fake thread, doesn't exist. But each of these yellow blocks is chunks of JavaScript execution. And from a long task perspective, we're going to see 4 of them. The 200 millisecond one, the 150 millisecond task, the 300 millisecond task, and the 100 millisecond task. Now, as far as the API is concerned, we are never going to find out about the 20, 40, and 15 millisecond tasks. Partly because anything under 50 milliseconds is a little less concerning. More so because if we get too granular with the timing, if we start to give too precise of timing information for those little ones, we start to open up all sorts of security issues, and people can do all sorts of timing-based attacks to figure out where you've been and what you're doing, and it gets bad. Security things mess things up all the time, bad folks. So there's different ways that we can look at this data and track this data. One would be to look at the number of long tasks. This is presented in speed curve. You can also get this in impulse, which is Akamai's RUM product. And in that case, the metric's just, in this case, going to report 4. So if we're tracking that, we're going to see 4 tasks. We don't know how long they took or anything like that. Longest long task is another way of presenting this. Again, speed curve surfaces this. I don't know how many other RUM products do. I haven't seen it in most of them. But to be fair, sometimes finding things in a few of them can be a little tricky. But in this case, this metric would report 300. So we wouldn't know that we had this total. We wouldn't know about the other tasks. We just know we had that 300 number. The most common way I've seen it presented is long task time, as Impulse calls it, or JavaScript CPU time, as Speed Curve calls it. This is the total of all of these long tasks. So we're going to take our 200 plus our 150 plus our 300 plus our 100 and get 750 for the total metric. This is the most common way I've seen it presented. Lighthouse has a little bit of a variation that they're introducing with total blocking time. It sounds similar. It sounds like it should be the same thing as what we just saw, but it's not. It doesn't give you the total. It just gives you the time over that 50 millisecond threshold. So if you look at the name and kind of break it down, it kind of makes sense. If we assume anything 50 milliseconds or less is non-blocking, then the total blocking time is the stuff over that 50 millisecond threshold. So again, from this perspective, total blocking time isn't going to give us 750 milliseconds. It's going to ignore that first 50 millisecond chunk and give us 550. It's another way of looking at it. Any run provider or anything that you'd be monitoring could give you this information as well. Honestly, I'm not quite sure yet how I feel about it. I feel like I kind of just want the sum number. And I also worry that there's going to be some confusion. Lighthouse is a huge influencer when it comes to what metrics folks adopt. And I suspect there's going to be people wondering why Lighthouse is reporting certain, things for total blocking time, and speed curve or impulse or whatever it happens to be has a different metric. Like the numbers are very different, even though it sounds like they should be the same thing. That being said, it's just the way the data is presented. They're both telling you the same general information in the end. My advice, because long tasks are such a new thing, and with any new metric, you always want to tread a little cautiously. But if you have access to this data, check how it correlates to your business metrics. In my experience, long task time or JavaScript CPU time has the strongest connection. The number of tasks sometimes connects, longest text sometimes connects, but long task time, pretty much every single time I've ever been able to plot it against a business metric, it connects, it correlates. So I highly recommend that as a solid starting point. I also really liked the way that Andrew presented this this morning. I love this idea of meta metrics. Like if you have your supporting metric or your major metric here being total blocking time or JavaScript CPU time or whatever it happens to be, I love how he took these other ways of looking at it and presented them as these sort of additional supporting metrics that help you to understand exactly what that big metric is actually telling you. So I think that's another very, very smart way to look at it. But yeah, inside of any RUM tool, you should be able to make some connections here. So this is one client I worked with. This is their impulse chart. It's showing conversion rate, that's your yellow, versus long task time. So you can see as long task the amount of time gets longer and longer, that conversion rate sharply drops off of a cliff. Speed curve has a similar, again, here we're connecting the JavaScript CPU time, same metric, against bounce rate. And we can see that as the CPU time increases, the bounce rate starts to steadily go up. So it's become to the point where I find it's pretty predictable. Like I can probably say with most certainty that for most of you, if you're tracking long task time against any of your business metrics, you will see a connection there. So I think it's a pretty safe bet to be paying close attention to something like that. So we know that right now we're passing a lot of JavaScript down. I hope we kind of all agree it's too much. We know that it has an impact on business. We know that it's leaving folks out. So the next question is, if this is bad, what is good? Like, how do we figure out what good looks like? How much is too much? So let's science this up a little bit. Think about the last time you upgraded your phone. For some of you, maybe this last month, maybe 6 months ago, maybe a year ago, maybe 2 years, if you're really pushing it. The average US consumer upgrades their phone once every 32 months. So that's almost a full 3 years between new devices. Most people are not running the latest equipment, nor are they running the most powerful. Most people aren't sitting there with an iPhone 11 or a Pixel 4 or whatever it happens to be. According to Statista, the average purchase price of a smartphone is $214. And this number is greatly inflated, by the way, by the people who do pay for the iPhones, like the folks who took out a second mortgage to get the iPhone 11. You take those folks out of this, and this number drops down below 200. But even the iPhone adoption, it's, the amount of folks using it, something like that, it's less common than you might think if you were to just judge by our own tech community and the prevalence of iPhone devices there. According to the IDC, global shipments of smartphones, 85% of those are Android devices. So if we were to put all of this together and sort of create a user profile of like, what does an average person using a mobile device to access the web look like? Well, we'd have to say they're probably using an Android device. It's at least a year old, probably older, and it probably costs them less than $200. You can confirm this too. Like one of my favorite things to do to figure out like what my next test device is going to be is watch the Amazon bestseller lists. You can see what folks are looking at and what they're buying. So this is admittedly, I haven't updated checked recently. This is a couple months old. But at the time, if you look, the only device that's over $200, you have to go to the 8th best selling phone to find something. I particularly like the $30 track phone that was the 6th most popular, because that thing's going to be just amazing to browse the web with. But no, this is a great resource. It's a fantastic way if you're ever curious to like build out what that next test device should be, looking at it, you could do a lot worse than looking at a bestseller list and just buying your cheapest device there or a mid-tier device. I'm a huge proponent of testing your site on the crappiest, cheapest devices you can possibly get. You know, I've got several of these like Alcatel 1X and similar devices lying around that are just brutal using anything on the web, but especially anything that's powered by a significant amount of script. The more powerful the device, the more likely it is to hide those performance issues, particularly ones related to JavaScript. So we want to make sure we're doing some stress testing. So if we start with that baseline, that Android older than a year, less than $200 baseline, and then Alex Russell, who works at Google, did this in a post, and he actually added this sort of variable of the network in, a slow 3G network based on global connection data that shows that we've got a lot of 3G traffic. And even when we have 4G traffic, it's often very highly congested and much slower than we'd like to see. So if you use a slow 3G network and this sort of, you know, default type of device as sort of our guideposts, what Alex did is he did a little bit of math and he realized that that means we have about 130 to 170 kilobytes of critical resources if we want to reach a 4-second timed interactive, which seems like a reasonable threshold to try to aim for, 4 seconds to get the page to be interactive and usable. Now, this is critical path resources, so this means we're not talking images or fonts. We're talking about things that stand in the way of that initial, you know, critical path and rendering process. So that's your CSS or HTML and your JavaScript. So that does mean that you don't have 130 kilobytes to spend on JavaScript. You got to spend some on HTML and CSS. So if, you know, and the more you're spending on JavaScript, the less you have in your overall budget. But I'd say a fairly conservative number, like, I don't know, trying to be nice, would be to say that maybe we can pass 100 kilobytes of compressed JavaScript over the network and still hit this target. So that would be our overall number. But then what about individual bundles? That's another thing that comes up often. As people are building a JavaScript-driven site or application, you're using Webpack or Parcel or Rollup to create these different bundles, and you try to be clever about the size and when you're pulling those in. You know, how big is too big when it comes to an individual bundle? Now, again, I think we can science this up a little bit by looking at script loading behavior, specifically in V8, which is the engine that powers, you know, Chrome and Edge and things like that. Or I'm sorry, yeah, Chrome and Opera, or, you know, those sorts of browsers. So here's how it works. We're parsing HTML. We come across a JavaScript file that we have to parse and compile. Now, traditionally, this all happened on the main thread. So we download the file. We then, after we download, we move on to parse and compile. After we parse and compile, we're able to execute it. All of this blocking the main thread, obviously not a good thing. It means we can't respond to user interactions. So most engines, V8, SpiderMonkey, which is used in Firefox, if it's above a certain size, will try to move that parse and compile now onto a separate thread whenever they can. So that means that what we have is something a little bit more like this. We still have this linear progression. We still download and then parse and compile and then execute, but at least we've offset that parse and compile time so that we have a little bit of window where the browser could respond to user interaction or do other work. Now, the one thing that was always a bummer here is that you had to wait for the entirety of that script to download before you could start parsing. So if you're passing a 200 kilobyte script, you have to download the full 200 kilobytes before any parsing work could happen. That's no longer the case anymore, not necessarily. Script streaming, which is a feature in V8, it's not in SpiderMonkey yet. They've talked about it, but they're also kind of working on building a whole new parser, so it's been deprioritized for now. But with script streaming, what happens is the browser said, hey, let's not wait until the full file is there to start parsing. Because as it's coming back from the network, we're getting chunks of this file at a time. And parsing JavaScript is a pretty linear process. So instead of waiting for the full file to start, let's wait until we get 30 kilobytes or so. And once we have 30 kilobytes, we can start to parse that 30 kilobytes while the rest of the file is coming in over the network. So what this means is that we're now able to move the parsing time mostly in parallel with the download time. It's no longer this sort of linear progression. We actually get a little bit of stuff happening at the same time here and speeding things up. And because parsing is so quick, so often after the JavaScript is downloaded, we're fully parsed very quickly after, and execution can happen soon after. So we've sped up this entire process. Now, where this gets interesting to me is when we look at the combination of this benefit of separate threads as well as the streaming and being able to move the parse in parallel. So let's say we have two different scripts, a.js and b.js, because I'm very creative when I name things. What we can do now is the browser is going to open two different threads to handle the parsing of these different scripts. As long as those scripts exceed the 30 kilobytes and as long as they're loaded in a way that lets them pull it off into another thread. Things like async or defer guarantee that. I think not some non-async and defer stuff can be moved off under certain situations, or at least they've been experimenting with that. I'm not 100% certain exactly how that works yet. There's a V8 expert in the chat room. Jump on in. But what this means, so what is it? This means that we now can actually have two files downloading in parallel and parsing in parallel. So we're really offsetting a lot of that cost. So the first off, I want to make it clear, the takeaway here is not like script streaming is great. Let's make sure that if you have a script that's a little smaller than 30, you artificially inflate it to get script streaming. No, that's not what we're doing here at all. There is a little bit of overhead communicating back and forth between these threads anyway. So it's not free, this entire process. There's a reason they have a cutoff at some point. But the takeaway is instead of one massive 200 kilobyte bundle, we're going to be better served by serving two 100 kilobyte bundles, for example. Because now instead of having this one file that's kind of doing the work, all, parsing and download is still happening in parallel, but it's happening for the entirety of that 200 kilobytes. Now we can actually open up that separate thread and have things like the full 200 kilobytes being parsed much faster in parallel, which is not a thing, but I'm going to run with it because why not? So you get the idea, right? We're speeding things up if we break these bundles down and take advantage of that script streaming functionality. Now 30 kilobytes, again, there's a little bit of an overhead in communicating back and forth between the threads. So maybe 30 isn't the perfect target. I think it's reasonable to give yourself a little wiggle room. So I would say to maximize the benefits of parsing and script streaming, we probably want bundles that are going to be in a 50 to 100 kilobyte per bundle range. Anything larger than that, you probably want to start breaking down. So again, we're looking at 100 kilobytes total and per bundle and no more than that 100 kilobyte threshold, somewhere between 50 and 100. These are not conservative targets. They're targets that are going to help you hit like meaningful performance metrics. If you can get a timed interactive of 4 seconds or less, you're in great shape. They're targets that are going to help your company be more effective and profitable. They're targets that are going to open up your site to new audiences that may not be able to use the site otherwise. But they're not easy targets to hit. And certainly anybody who's watching this right now with an existing code base and you're looking at these numbers, you're probably ready to kick me off. Or maybe you've already left because you're like, no, I'm not listening to the rest of this. They're great numbers, but most of us don't get to start with a complete fresh reset. Most of the time we're coming at it from the other end of things. So if you're listening to this and starting to break into a cold sweat at the idea of trying to whittle down a multi-megabyte JavaScript payload to these targets, I get it. I do. Most companies I work with are at that end of things. They've shipped it out. It's multiple megabytes of JavaScript. And now they're trying to figure out, well, how do we fix the performance issues that we've seen? So more often than not, you're not starting fresh. You're trying to whittle. Now, I could, if we were going to try to do a comprehensive, like how do you reduce the size of your JavaScript talk? I mean, frankly, that's a multi-day conversation. But I did want to give you a concrete example from one company I worked with who started out with a 2.6 megabyte vendor bundle. So vendor bundle being, they bundled all of the different scripts from third-party sources like their vendors into this one massive bundle. So 2.6 megabytes on the device, 487 on the network. Ignore for a second, if any of you are like really up on your bundling stuff, the vendor bundle is probably not the best approach anyway, because what it does is, as soon as one third-party script changes, your entire massive vendor bundle gets evicted from cache because the browser sees it as one file. So you probably don't want it chunked up that big anyway like that. But in this situation, what we did is we tried to move forward and see how could we reduce the size of this bundle. So there are a number of different tools, 5, 6 different ones you can use to analyze the bundles that are generated by Webpack. There's similar tools for Parcel and Rollup. So if you're using one of those things exist. My favorite from Webpack is still Webpack Bundle Analyzer. It gives you this sort of, you can zoom in and out, and it's got these nice colored boxes. And the boxes are weighted, like the size of the box varies depending on the size of the actual script. But it shows you the contents of whatever was generated in those bundles. So when we looked at this, the first thing that jumped out is what you see here, AWS SDK. Yeah, that's 1.8 megabytes of parsed JavaScript, 244 kilobytes on the network just from this vendor library alone. Unfortunately, so one of the things that Webpack or other bundlers give you is this benefit of tree shaking, which is this idea that, hey, if you got unused code, we can kind of shake it off, Taylor Swift style. That was just stupid. And leave it out of the actual bundle that gets outputted. But you have to use ES modules for that to work. AWS SDK uses a common JS approach, which means we don't get tree shaking. So we have to pull this entire massive thing in, and we can't shake the weight off. So it turns out, though, that in their documentation, on a page that's in the middle of this very long list of pages, and in the middle of this very long page of words, there is a one-line sentence about pulling in just what you need and how you can pull in an individual service instead of the entire library. So for us, what that looked like was we had this before, where we were importing the services we needed from AWS SDK, but it brings in the entire thing. We just had to switch to actually detailing specifically which service, which provider we wanted to pull in by sort of, providing a more detailed route. And this was, I think, a 2-line change. So I think we made this change, and then we had to change one thing about how it was referenced later on. But this 2-line change took that 1.8 megabytes down to 194 kilobytes. That's a 1.675 or 1.675. 1.65 megabyte reduction from a 1-line change. So the lesson here is it pays to read the documentation, even if the documentation is extremely verbose, and even if the information you actually need is hidden very, very deeply inside of that verbose documentation. Now, sometimes you get big wins like this. If you have a very large bundle, in fact, like if you have a bundle that's, in any sort of megabyte range, I'm betting you have some big savings. We probably have a few things you can shave very quickly. But most of the time, performance improvements don't happen in one big, massive chunk. Unfortunately, I wish they did. Most of the time, it's more a matter of chiseling away. And so that's what we kind of did after this. So again, looking at the bundle analyzer, we saw View Apollo, 52 kilobytes seemed a little excessive. So we went to this fancy tool called Google, where you can type in a query and it tells you what other people are looking for too. And it turns out that everybody's been complaining about View Apollo. And so on GitHub, we saw that there was already work done on a newer version of the library to reduce the size. So what they did is originally they had these other dependencies they were pulling in that were getting bundled into the View Apollo script. So they changed their process to mark those as external. So what this means is that they're using rollup, but it would work the same for Webpack or whatever. It has the opportunity to say, hold on, I don't necessarily want to, I'm going to be pulling those from an external source. I don't need to bundle this into that one big JavaScript file. You can be a little bit more intelligent about how you're pulling things in. So we upgraded the version. We had to upgrade Nuxt Apollo. That was what was actually pulling in View Apollo. But once we did that, we got that down to 27 kilobytes. So a 15 kilobyte savings, not bad. The next thing that jumped out at us was this UI.common.js, which is 520 kilobytes. This is Storybook. It's a very popular UI components, helper thing. And again, this was a Vue app, so it was Vue Storybook. So this was a Vue Storybook instance, and all of these components running in this other build process were being pulled into this one giant file. So what we did is we ran Webpack bundle analysis on that build process on the Storybook instance to see what was actually in there. And it became very obvious why this file was so big. Vue Swiper, it turns out, is kind of massive. But you'll notice also that like the actual components is a small subset of what this massive file actually ends up being. Most of this is vendor scripts. And if you've got a keen eye, and Zoom's resolution isn't too bad, you'll see that there's core.js pulled in a couple different times. We have Lodash coming in a couple different times. I think there's like Beautify or there's a few of these sorts of third-party scripts that are actually bundled several times within this one big bundle. The challenge here is that, so this build process, because it's not pulling those out and not properly figuring out we only need one version or marking things as external, it creates this one giant JavaScript file. So when it's consumed in the main app can't do anything intelligent with it. It can't say, oh, we're already using core.js, I don't need to put it here. Because as far as it's concerned, all it's got is UI.common.js. So what we needed to do was we needed to prune this down so that the main app could make better decisions about what to pull in and what not to. So the first thing we did was we used Webpack aliases to make sure we only had one version of core.js. Now, Yarn and NPM, if you're using either one of them, they both feature deduplication, which is supposed to try and eliminate the fact that you'd have multiple versions of the same library being pulled in. It doesn't always work depending on how things are kind of pulled in, differences in versions. So in this case, what we use is the Webpack alias. And we said specifically, anytime you see core.js referenced, use this version that's located directly in the node modules folder. So if anybody else, any other libraries pulling core.js in, we're going to point it to this one instead. So we get one version. And the other thing we did was, again, we recognized a few libs in here like ViewSwiper, Viewlidate, things like that were already in the main project. So we needed to tell this build process that we were going to pull them in from an external source. So just like what ViewApollo did, we marked them as externals. We said anytime you see ViewSwiper or Viewlidate or these Viewlidate validator things, we're going to pull those in externally. So you don't need to worry about bundling those into this big bundle. We're going to let the main application deal with that and pull those in and deal with it at that level. So once we did this, once we handled the aliases and marking these as externals, we brought the size of the UI.common script down by about 60 kilobytes. Again, not 1.6 megabytes, but not bad. So from this short list of things that we did, we were able to bring the vendor bundle down from 2.6 megabytes to 898, a 66% reduction. Now, based on everything you've heard today from me and from everybody else, obviously we'd love to be smaller than this, right? But the rest is a process. There has been additional work. There has been additional weight shed. But this was most of the low-hanging fruit. So after this, it was things like refactoring some of the components themselves, tweaking the bundling strategy so that we approach splitting a little bit differently, reassessing certain things that we were using and trying to find alternatives. Again, there are a few overnight success stories in performance. When they do happen, we love to tell them and everybody loves to hear them. But I also think we got to be careful, be realistic, because most of us aren't going to find one change that's going to cut 4 seconds off our page. It happens sometimes and it's awesome, but usually it's just a little bit here and there, which is why I think one of the most important things you can do is focus on how do we maintain and then iterate. It's always deflating when you make massive improvements and then they regress. And if you're not doing anything other than fixing these issues from a coding perspective, you are going to regress. The other problems are going to come back and they're going to resurface. It's critical to lay down the supporting groundwork and infrastructure and culture to help keep the weight off and get to a point where we're making it lighter, like we're progressing forward in the right way versus going backwards. So here's how I like to do it from a JavaScript perspective. And it's, in an ideal scenario, I want to be warned or blocked when I install a library. I want to be warned or blocked in my code editor. I want to be blocked if I try to submit a pull request and things are too heavy. I want to be blocked if I try to do a deploy and things are too heavy. And if I do manage to get a deploy out, I want tracking and monitoring so that I'm able to look back and see exactly how that's impacting the folks coming to my site. Now, I know it's a lot and it seems maybe a little bit aggressive, but it's the way I like to do it. And I think it's sort of echoing what Melanie was saying earlier about this importance of shifting left into that developer workflow. The more checks and balances you have, the better. And the closer you do it to where the developer is writing code, the better. If deploy is the first time I'm finding out things are slow or things are not performing well, then at that point, I've done a ton of work. And now I have to go back and try to refactor it all. I'm going to get really frustrated. I'm going to miss deadlines. That's where you start to cut corners. And that's where the business might say, oh, we'll come back and fix the performance later. And that's how you get right back into the situation you were in. But if you can catch me writing code at the very beginning, like as I'm writing the initial code, as I'm building the feature, as I'm installing the library, I can avoid the issues altogether before I sink a ton of time and energy and resources into it. And it's very achievable. I don't know how many people have seen Bundlephobia. It's a fantastic site. Love it. Where you look at NPM modules and you can get information about the size of that module, gzip versus parse, approximately what it means to download that, if it's tree shakeable. You also get information like similar packages, alternatives that might be lighter. So one thing you hear a lot about, if you've ever read anything about bundle analysis or improving bundle size or SON talks, Moment.js or Lodash, those two get tossed around a ton. Specifically for Moment, it's swapping it for something like DateFNS or something like that. And those are good optimizations. And this is something where if I have this data presented to me up front, I don't have to switch. I just build my app that way from the start. And I can use this to guide my decisions. So there are tools that are built on top of Bundlephobia that help with this. There's Bundlephobia CLI, which has a Bundlephobia install command. What it does is it'll apply a size limit to any library you try to install. So in this case, there's a size limit of 100 kilobytes, and we're trying to install AWS SDK, and it's telling me, nope, can't install it. It exceeds your budget. This is configurable in package.json, so you can set custom size, to whatever you want it to be. Now, if you want to install AWS SDK, like you absolutely need it, you can still do it. But now you have to run the command in interactive mode and explicitly say, I'm okay with doing this, even though it exceeds my threshold. Which you want that functionality available, but this makes it a very conscious decision. Then in the code editor, there's a thing called import cost for VS Code, where anytime I'm importing a module, it's going to put as a little aside there what size I'm actually adding to my, when I'm doing this. Like, oh, I'm adding 68K by including view. This doesn't stop me from doing anything, but it provides contextual information at the moment where I'm writing the code, so I can at least get that information presented to me in a way that I'm seeing it and aware that I'm making that decision. And then, of course, on the PR, we've seen there's countless examples of different tools like Bundle Size or Bundle Buddy. This is Bundle Size that you can integrate with your continuous integration environment or GitHub to warn or break the build if a certain threshold is exceeded. You'll notice that, by the way, that Bundle Size does provide a threshold here, like there's a limit, but there's also a little bit of a wiggle room here. That's important. There's one company that was talking to about how they had rolled something out that broke the build if things got too heavy, but they didn't include a threshold. And so the first developer who ran into it found out that their package size limit was exceeded by 82 bytes and broke the build. It was a rounding error, so they fixed that. But then the next person who ran into it, their build was broke because a sub-dependency change that added 1 kilobyte of JavaScript. So a little bit of wiggle room to sort of prevent that kind of thing is important, but still having something that's breaking that process before, so that you stop this heavy stuff from going out ever is a really important part in making sure that you don't regress. It's all about introducing healthy friction into the process. Modern tools do a great job of reducing friction and making it all too easy for us to add whatever we want to our sites and applications. We want to change that. We want to add some healthy friction. We want to make it hard to do the wrong things and easy to do the right things. Sir Hawksworth, he gets really mad when you drop the sir. I really liked this tweet that he was posting in his talk where he was talking about, what did I do to make this so fast? Nothing. I just didn't do anything to make it slow. Right now, our default stance is the opposite. Our default stance makes it very easy to add more and more JavaScript to our apps. It's literally an NPM install away. We need to flip the script and make it difficult to ship something that performs badly. If we've built a web that dismisses the affordable, typical Android device, the lower powered networks, and the people that use them and that are on them. And I don't think that we've done this because we're bad people. I don't think we've done this because we don't care. It happens because we can. It happens because the technology that you and I use every day can handle it. But not everyone's technology can. Our technology doesn't have the constraints that, technology that years ago did. We don't have to worry about 4 kilobytes here and there, which is why I think it's so important that we find ways to bring those constraints back into our process and back into the tools that we use, so that we're constantly being encouraged to chip away at the piles of script that we're using right now, and that we build these faster and lighter experiences, and that we keep them that way. Thank you.